Great. Thank you so much for the introduction and to the hosts and to Dr. Goris for such a fantastic talk. I'm really excited to be here and share some of our group's newest work on coccidioides in Utah. So no vaccine yet exists, and that means that the current prevention strategy that we have is to try to raise awareness so that people can try to reduce exposures when possible. This is challenging though, because we don't quite know where the fungus exists, as Morgan highlighted. And this current CDC risk map is drawn from skin testing studies that were largely done in the 1940s and 50s, and then updated more recently with public health surveillance data. So not only do we not know exactly where the fungus is, but we don't know what the impact of rapid climate change and land use change will be. And in Utah, we're uniquely positioned to study the distribution of the fungus because we are at the edge of the current predicted endemic range. And this is a place where systematic environmental sampling hasn't yet been done. So one example of the poorly understood risk of coccidioides is a 2001 outbreak that occurred in Dinosaur National Park, Utah, so not far from where my lab is in Salt Lake City. And this outbreak was among people working at an archaeological site, and many of the people who sifted through dust as part of the excavation became sick. The startling part was that Dinosaur National Park was 200 miles north of what was at the time, shown here in gray, thought to be the endemic range of the fungus. So to start to ask, where can the fungus exist in the field, and to identify climate and environmental factors associated with the distribution of coccidioides in Utah, we began our sampling in Washington County, which in the map here is the southwesternmost corner of the state. It's where incidence of reported valley fever is highest in the state, although we think there is significant underreporting as compared to California and Arizona. And this is a map done by one of my students, Jacob Sussman. So Washington County is also unique because it's the home of St. George, which is the fastest growing metro area in the United States. It's the #2 city in the US for construction jobs. And this picture here is of the ongoing construction of Black Desert Resort. So this is a luxury golf course that, as you can see, is being cut into previously undisturbed Mojave Desert landscapes. So this rapid development that is happening across St. George is increasing the interface between humans and relatively undisturbed land. And this puts people at risk. Construction workers, of course, are at high risk of infection because their work involves this large-scale excavation of soils that might contain the fungus. Our sampling leverages a stark elevation gradient in Washington County, and this spans Beaver Dam Wash, which is Utah's lowest point, and goes to the top of Signal Peak, which is the highest peak in the region. And I've developed this sampling with Kevin Perry, Eric Rickart, and Katrina Derrig. And as you can see, we're not only collecting soil samples, but also collecting small mammals. And the benefit of sampling along an elevation gradient is that we can efficiently, along a 50-mile transect, sample many different microclimates and habitats. So we've conducted spatially stratified site selection along this elevation gradient and spanning 3 different ecoregions. And these are 2 of my undergrads, Eamon Miles and Evie Adams, and they're collecting soil from small mammal burrows. And Bridget's lab has shown that small mammal burrows are more likely to be positive for the fungus than adjacent soils. We are testing soils with a cocci-specific qPCR, and then we're using random forest models to ask if we can explain the site-level prevalence of coccidioides. We're also using spatial regression models, and I'm not going to talk about that today. So turning now to the results, in gray is the state of Utah with our sampling sites in red. So again, focused on Washington County, and then blown up. Unfortunately, the points did not come through on this map. So unfortunately, you won't be able to see the positive sites, but along this elevation gradient, we found more than 6% of sites, 6% of samples are positive, and that includes 39% of the sites that we've sampled. Apologies that the map did not come through. So we found Coccidioides in southern Utah, and then we wanted to know what are the environmental variables associated with its presence. And this was led by Emmanuel Fonseca, my postdoc, who is also here at the conference. And we first examined univariate box plots just of a set of uncorrelated environmental and ecological variables. So we excluded any covariates that had more than 70% cross-correlation coefficients. And as you can see here, so here we see the distribution of measured environmental variables at negative sites in blue and positive sites in red. And here you can see that vapor pressure deficit is higher at the positive sites. And as a reminder, this measures the difference between the moisture the air can hold when saturated and how much it does hold. So the positive sites are drier. We also found that soil coarse fragment content is higher at positive sites. And this measure is the fraction of soil particles that are greater than 2 millimeters in diameter. So to examine these relationships more closely, we moved away from just dividing these sites into binary, positive or negative, and instead looked at the prevalence of Coccidioides across these sites. And unfortunately, the error bars did not come through, but in these, again, univariate negative binomial models that are zero inflated to account for many sites not having Coccidioides presence, we found that we can see a strong impact of elevation on Coccidioides prevalence and a possible threshold effect, under which there's very low prevalence of Coccidioides at any site above 1,300 meters. So then we took advantage of these environmental covariates and we used them in random forest models to then predict positivity at individual sites. And this plot is constructed, it's called a feature selection plot, and it shows the variable importance for all of the covariates we evaluated for inclusion in our random forest model. And the covariates are ordered from left to right in order of their importance. And any variables in green are significantly associated with Coccidioides presence. And to account for spatial location, we included covariates and principal components that accounted for latitude and longitude of a site. We use this plot to then select covariates for our final model, and the importance of these covariates is shown here. So again, we see vapor pressure deficit and the soil coarse fragment content are the most important in this model. So how well do our models perform in predicting presence or absence of Coccidioides then? So this receiver operating curve is one way to summarize the sensitivity and specificity of a classification model, and a curve that's closer to the top left corner of the plot indicates better model performance, and the area under the curve summarizes the overall model performance. So specifically, this measure of the area under the curve measures the model's ability to rank sites that are positive more highly than negative sites. And another way to evaluate our model, of course, is accuracy, and we have a 75% accuracy. So we're performing fairly well. We wanted to ask also, because we're continuing to collect field data and my undergrads are continuing to collect more sites, we're waiting for more qPCR results to come back. So will more field collections improve our model predictions? And to ask that question, we subsampled our data and then fit random forest models and measured AUCs again. So in the different colors here of the the RUC curves, they represent different subsampled proportions of our data. And what we see is that AUCs decrease when we give the model less data. So we predict that doing more field work will help us better predict where Coccidioides can exist. So we're continuing to sample across this diverse ecosystem and include more covariate data in our models. And I'll look forward to suggestions from the audience of what other covariates we should include. And in summary, we found moderate prevalence of Coccidioides in this very fast growing metro area. And we identified soil and climate properties associated with the presence of Coccidioides. And we need to continue collecting our field samples. So this is work done by a big team and a very interdisciplinary team who I want to thank, and thank you all.
Are there any questions? Come on up to the mic.
Great talk. I'm curious, in your climatic variables and soil variables, is that a bulk of the entire site, or are you specifically looking at like the soil properties of a positive sample?
That's a fantastic question. We aim to do both. Right now, we're just we're just trying to model site level prevalence, and we're using environmental and climate variables that are from these publicly available data sets. But we also want to go to the soil samples themselves and look at soil silt content, coarse fragment content, those kinds of soil properties to create a two-level hierarchical model for both site and sample level positivity.
Cool. Thank you.
Thank
Great
you.
talk.
Hi. Question about the, I know your things didn't come through on your graph, but I noticed the elevation and you said 1,300 meters. So does that mean if you're, what do you do, multiply times 3 to get feet, something like that? So if you're around 4,000 feet, you're good and you don't have to worry too much about Cocci? Or?
That's a great question. And probably similar to the discussion at Morgan's talk, probably elevation is also correlated, we think, with vegetation definitely, and then also what rodent species are at that vegetation. And we can see it when we go to these different sites. They're completely different vegetation mixes, and it just changes as we go up Signal Peak.
Got it. Thanks.
Thanks so much. There's no questions online. That was a great talk. We're going to keep our eye on St. George.